kind of switch up with algebra. After chapter 3, we kind of forget about solving equations for the rest of our time almost. We'll continue in this course to have problems on our tests involving solving equations and inequalities because it's important to just keep up our skills with that. And every single test moving forward will be more cumulative. So the next test we have, we're going to have questions on solving inequalities and solving equations. But you'll notice, like, moving forward, we're going to get into different stuff in algebra. Lots of graphs and manipulations of graphs and stuff like that. So this is kind of like an intro chapter to like the next phase of algebra. We go from solving stuff, and now we're going to transition into graphing stuff. All right? So let's talk about graphing. Types of graphs. Graph examples. We could have graphs with just dots. Okay? We could have graphs that are curves or lines. Okay? These are all points, all right? And we call this a finite amount of points. Finite as in I'm able to count them. Finite amount of points. What's interesting is that curves or lines are actually an infinite collection of points. So what creates this curve is actually a bunch of points. However, we have so many points that as we plot more and more points, they start to connect. And you start to see these gaps getting filled in. And before you know it, it's not that you can see points, you just see a line. A line being an infinite collection of points. All of a sudden, it's not a point after a point. It's just what looks like a line. So a line or a curve is an infinite collection of points. Or an infinite amount of points. Okay? Now on a graph, we have these axes. Okay? The horizontal axis is the x-axis, or the axis. Vertical is the y. Now we can label these axes depending on what we're graphing. So this could be money, and this could be tickets bought. Okay? And what we typically do when we're talking about this graph and this relationship is we'll say we have our y compared to our x, or our y versus our x. So this graph example of is money versus tickets bought. We won't say it's tickets bought versus money. We always do our y first versus our x. Okay? Now, something like this, the x-axis could be like time. The y-axis could be something like distance. And this would be distance versus time. Distance, my first thing is going to be on my y. The second thing will be my x. Okay? Now there's another way we can call these graphs besides like a finite amount of points or an infinite amount of points. Okay? And that's continuous or discrete. If we have just a finite amount of points, we consider this to be a discrete graph. And an infinite collection of points, we call this continuous graph. Continuous. Okay. Notes today are going to be a lot of me talking, a lot less of you doing, but moving forward, we'll start doing more. All right, so let's do a couple examples. Temperature versus time of day. What is going to be the label on my y-axis? Will it be temperature or time of day, Mr. Miller? Temperature. Temperature is the first thing. The first thing typically goes on my y-axis. That means time of day is going to have to go on my x-axis. Now let's talk about maybe today's temperature. So we'll have a graph that starts maybe at 12 a.m., which is midnight. Then we'll have 6 a.m., so a little bit before now. We'll have 12 p.m., noon. We'll have 6 p.m., and then we'll kind of shoot right back up to 12 a.m., okay, to next day. All right, so it's been muggy, it's been kind of humid, temperature haven't fluctuated much. Why don't we say this is 50 degrees and we'll go up by 10, 60, 70, 80. So last night it was probably around 70, maybe even higher. And this morning it was about the same temperature. Well, as we go through the day, like noon, it's going to probably get a little hotter. But all of a sudden, a cold front's going to roll in. And by tonight, we're going to see in the 60s. And by midnight, we're going to go down to the 50s. So it's going to be a cold night tonight. Okay, now those are just random data points that I plotted. My question is, should I keep this graph as a discrete graph with just a finite amount of points, or should I probably connect them to show an infinite collection of points? What do you think, Ms. Cordova? Yeah, let's connect them and maybe not put arrows on it. Let's see. So why am I connecting them, Ms. Cordova? Exactly. Because we're dealing with time here. Okay? We will have a temperature at 1 o'clock. We'll have a temperature at 1:05. We'll have a temperature at 1:30. So we need to show that there are temperatures there. There's an infinite amount of temperatures that could be collected in any given day, depending on what second or what millisecond you're looking at. Interesting, Miss Page? Yeah? All right, great, great. I'm glad you're enjoying your time here. Now, let's label this graph as money spent and raffle tickets bought. Correctly label your axes, your Y, and your X. We should have money on the Y. We should have tickets bought on the X. Now let's talk about those ACL raffle tickets that you could have bought. So one ticket was worth $5, right? So I could buy 0 tickets. Let's say 1, 2, 3, 4, 5, right? Well, if I bought 0 tickets, I spent $0. If I bought 1 ticket, I spent $5. I bought 2 tickets. I spent $10. 3, 15, 4, 20, and 5, 25. Okay, interesting. Looks like we have what appears to be a line starting to form with these data points. Now my question is, should I connect those dots? It looks like it wants to be a nice line. What do we think, Mr. Mueller?
I think that we should put a line with it.
Yeah, so you think it looks like it wants to be a line, so connect them, make a line. Yeah, I think that makes sense. What do you think, Mr. Moan? Do you agree?
No,
Why not?
because it's like 1, 2, 3, and like 1.5.
So you tell me you can't buy 1.5 tickets? Yeah, you're right. I can't buy 1.5 tickets, so I shouldn't have like a point here representing 1.5 and like $7.50. Okay? I can't buy 1.1 tickets. So, Mr. Mueller, you're right. It looks like it wants to be a line. However, in this situation, since you are not physically able to buy fractions of tickets, you're not going to connect. Okay? So while this first graph is continuous, the second graph is definitely discrete. And we can describe the graph. It just goes up a little bit, then comes down, or the money spent increases as the ticket you buy increases. But that's really less important than knowing that we do connect this one, we don't connect the next one. All right, this is interesting. Let's look at the second one. Speed of a car during a trip to Dallas. What should my y-axis or my vertical axis be labeled? Mr. Kidder, what do you think? Typically we saw like something versus something. I don't have that here. I just have speed of a car during a trip. So what do you think the y is at least?
Speed of the car.
Good, that's correct. What do you think the x-axis should be, Mr. Kidder?
Go to Dallas.
Yeah, it's tough. Like, how do you quantify trip to Dallas? I don't know. Let's see. If we're driving to Dallas, what does it, what's happening? You're driving, and what is occurring? What is passing? Besides, like, trees and, well, not trees, cows. Time. Time is passing. So it'd be speed relative to time. Okay? So, typically it takes like 4 hours, 3 hours, so we can do in hours. We could say it's 1 hour, 2 hours, 3 hours, 4 hours. Okay? We start out from home. Let's say this is 25 miles per hour. This is 50 miles per hour. This is 75 miles per hour. Just simple. If we drew a graph representing speed, it'd be interesting. It takes us about 30 minutes to get on the highway, to get on 35. During that time, I'm going to probably be going like 25, maybe 30. Okay? And maybe I'm on 620 and I'm accelerating. Once I get on that highway, boom, I'm up here at 75 and I'm going to go the speed limit almost the entire trip. Maybe I go down a little bit, maybe I speed up a little bit, who knows. But eventually we'll have to get off the highway, we'll have to slow down, and eventually we'll come to a stop at the end. So this would be a good example of what the speed would be on a trip to Dallas. For most of the time, you are going to be traveling at the same speed, around 75 miles per hour, the speed limit. You're not going to be steadily increasing or steadily decreasing? Well, if we did distance remaining, what would happen is we are not going to start at like 0, 0. This would be our distance, and again, this would be time. And we have 1, 2, 3, 4 hours. Distance is about like 200 miles. So this would be like 100 miles, 0 miles. Starting at 0, the distance remaining would be 200. And as I travel, that distance will decrease until eventually I get down to 0. Okay, both of these being continuous graphs because they're dealing with time. Whenever you have time, you can always find a data point at any second, millisecond, minute, hour that would produce an infinite amount of data points, giving you a continuous graph. Cool? That's 4-1. That's graphic. Check. Think you guys can handle it. We got discrete, continuous, infinite collection of points versus a finite collection of points. Let's get into some more mathematical stuff, like relations and functions, 4-2. A relation is just a set of ordered pairs. Okay, now let's talk about an ordered pair. Ordered pair looks like this. This is like 1, 3, 2, 3, 1, 5. This is an ordered pair. An ordered pair is an X and a Y. Okay? We can use it to plot points in 2 dimensions. Instead of having just one number line, we'll have a number line that's an X and a number line that deals with a Y. And we start plotting points in 2 dimensions. Moving forward, when we're graphing graphs, we will see that our solutions will be points rather than just like x's being equal to a number. Our solutions will no longer be like x equals 5. Our solution will be like 5, 2. That'll be a solution that we're going to plot. In this situation dealing with relations, it's interesting how we look at this ordered pair. We talk about x mapping to y, or x going with y. X goes with y. And what we're going to do is we're going to use something to help us remember certain things. We're going to say X is like a person and Y is like a bus. Okay? X gets on bus Y. Okay, just like how some of you, maybe most of you, get on a bus at the end of school. Your X, the bus number that you drive on, is Y. Okay? Cool? The reason why I talk about people and buses is because of this thing called a function. A function is a special type of relation. Where every X maps to only one Y. Okay? And let's think about the word function, or something being like functional. Something being functional is something that like makes sense, something that works, right? All right, well, let me ask you a question. Can multiple people get on the same bus? Yeah. So me and Mr. Miller, we live next door to each other. We're getting on the same bus. That's functional. That works. Can Mr. Miller get on 2 buses at the same time? No. Can Mr. Miller get on 3 buses at the same time? No. Okay? So when we talk about functions, we'll talk about these people on these buses. Okay? We'll say every person must get on only 1 bus. But multiple people can get on the same bus. Okay? Might not make sense to you now, but once we start looking at relations, it will. Okay? And there are multiple ways of showing a relation. This is the first way you can show a relation, a set of ordered pairs. Second way would be like a table. In a table, you'll have your x's and your y's. Your x's will be on the left, the y's will be on the right. And you're just going to list these set of ordered pairs instead of left to right. They'll be up and down. So 1, 3, boom. 2, 3, that's your next one. 1, 5. -5, 2. -4, 10. Okay, that's the first way. Easy. Second way, we call a map or a mapping diagram. What we're going to do is we're going to make 2 ovals, and we're going to make them big enough to fit numbers inside of them. Like this. Okay? It's important to not repeat. Okay? And what we're going to do is we're going to put our x's over here on the left and our y's over here on the right. So my x's are 1, 2, 1, -5, and -4. Well, I'm not going to repeat my 1's. I'm just going to say we have 1, 2, -5, and -4. And then we'll do the same thing over here on the right with my y's. I'll put down 3, 5, 2, and 10. Okay? Now, since we're not repeating, we can't just assume that these are going to go across. And that's not going to show us all of our relations, all of our ordered pairs. So what we do is we connect them using arrows to show which number goes with which. So 1 goes to 3. 1 goes with 3. 1 maps to 3. Person number 1 gets on bus number 3. 2 goes with 3. 2 maps to 3. 2 goes with 3. Person number 2 gets on bus number 3. The third one is 1 goes with 5. 1 maps to 5, 1 goes with 5. Person number 1 gets on bus number 5. -5 goes to 2. -4 goes to 10. Okay? And that shows the relationship between those numbers on the left and those numbers on the right. Okay? Finally, we have a graph. And with the graph, we'll have an x-axis and a y-axis. And we will plot these points on this 2-dimensional coordinate plane. Okay? And let's talk about how we graph points. It's important to know that the x is like your horizontal. How far you go to the left or to the right. Y is the vertical. Why I remember how to graph is you have to walk through the hallway to get to the elevator to go up in the elevator. Another thing I like to remember is you have to go down the runway before you take off. There are other ways to remember which comes first, the up and down or the left and right. Does anybody have any others from middle school? Any other like silly ways to remember? Miss Page?
Like if you draw a line, like it's sideways,
So if you draw a line right here, that forms a Y, so that helps you know that this is the Y-axis, kind of like that. Or you go all the way down and you have a Y and an X. Is it like that? Let me see. Let me see. Actually, let me see.
I just do it right here.
Oh, you do it over here.
From the top.
From the top right over here, and you can see this is a Y right there. See, that's another way to remember that's a Y. If you're a baby, you gotta, or if you're a kid, you gotta be able to walk first before you can jump. Different ways, but the plot, it's simple. Just go over for your X, go up for your Y. Over for your X, up for your Y. Over for your X, up for your Y. Over for your X, got to go through the hallway before you get on the elevator. Got to drive down the runway before you can run. Don't worry about -410, it's somewhere up here. Okay, but those are 4 ways to show relations. You got ordered pairs, you got a table, you got a map, you got a graph. All right, here comes the big question of the day. Is this a function? Yes or no, and why? You say yes, Mr. Jacoby. Why?
Because there's, like, for every X there's a Y, and it's not like 1 X, like 2 Y's.
I don't know. Look again. Anybody see differently? Mr. Stalker, what do you see?
There's more than one, yeah. I think there's more than one X Y, but I think that's right.
Let's see. Let's think about the buses. Multiple people can get on the same bus, but one person can't get on multiple buses. Mr. Jacoby, do you see now?
Yeah,
What do you see?
so 1 goes to 3 people.
Yes, the person 1 is trying to get on both bus 3 and bus 5 at the same time. Okay? Since you have this situation of one person trying to get on multiple buses, this is not a function. That's not functional. That doesn't make sense. One can't get on 2 buses at the same time. However, if this line wasn't here, 1 and 2 could get on bus 3 at the same time. That's fine. Okay? Cool. Why don't you guys do this one? I want you to express this relation, which is ordered pairs, as a table, as a map, as a graph, and answer if it's a function or not. Table are just lists of your X's and Y's next to each other. Maps are those ovals with the X's on the left and the Y's on the right. Your graph is just plotting those points. And then a function is a yes or a no question. Remember, do not repeat numbers with your mapping diagram. You should just have 4 and 5 in your map. Make sure we're going down the hallway first, up the elevator second. Down the hallway first, up the elevator second. All right, we should have these. Is this a function, yes or no? Yes is correct. Multiple people can get on the same bus. Person 0, person 1, person 2 can get on bus 4. It's fine. Person -3, person -2, person -1 can get on bus 5. That's fine. So that's good. Okay, let's skip this one, except I want you to look at this and tell me, is this a function? Yes or no? Everybody write down what they think. Look at this relationship and tell me, do we have a function, yes or no? Mr. Orsick, what do you think? No. I keep looking at Mr. Lake. Okay, why no, Mr. Orsick?
Because the one goes to multiple Y's.
Exactly. This X tries to get on all of these buses. This is impossible, so that's not functional. Okay, one way you'll also be able to see is using the graph. If you can draw a vertical line through 2 points, then it's not a function. Okay, it's called the vertical line test.
So basically, it's just like the two X's in the same function.
Yes. If you see 2 X's that are the same, it won't be a function. Unless they repeat the same point, but that probably won't happen. So if you can pass a vertical line through 2 or more points, then not a function. Okay, cool. All right, let's talk about domain and range. Domain is the x's of my relation. The range is the y's of my relation. We also call these x's my inputs, the y's my outputs. We also call these x's my independent variables, and these y's my dependent. And what we're going to do is we're going to memorize a quick little mnemonic to help us remember this, that domain is x's and range is y's. The mnemonic is Dixie loves Roy D. Okay? Like something drawn on a tree or something. I gotta work on my hearts. Not great. Okay? Dixie loves Roy D. Dixie stands for domain. I stands for input. X stands for X's. I stands for independent. Domain is your input, it's your X's. That's the independent. Roy stands for range. it deals with our outputs or our y's, and it's my dependent. Okay? Domain input x's, range output y's. Now to write down what a domain and a range is of a relation, it's pretty simple. We just say what is the D, or the domain, what is the R, or my range. Okay? We'll put this colon just to say my domain is, and then we will use these brackets whenever we have a finite amount of points. So this is 1, 2, 3, 4, 5, so we're going to have at most 5 numbers in my domain, and at most 5 numbers in my range. Now these brackets are funny. I feel like my brackets look like Jay Leno, because you have the hair, the nose, and the big chin. So think about drawing Jay Leno when you do these brackets. Hair, nose, chin. And all you do is you list off your x's for your domain without repeating. So my x's are my domain. I have 1, 2. I have 1, but I'm not going to repeat it because I already have it in here. I have -5, and I have -4. That's simple. Just the x's, the first values of these ordered pairs. The range being my y's, those will be my second values of my ordered pairs. 3, I won't repeat 3 again, 5, 2, and 10. Okay, and then you'd close your bracket. If you look at a map, the domain are the x's. Your x's are over here on the left. 1, 4, -3, 5. Range are the y's. 2, -5. That's it. And same thing for your table as it is for your ordered pairs. Okay. Rick, is this a function, the first one? Yes or no? No. One can't get on 2 buses. Is the second one a function? Yes. Multiple people can get on the same bus, but no one is going on to 2 different buses. The third one would also be a yes. Okay, we're going to skip the next 6, and we're going to find the domain and the range of a graph. Now the graph has an infinite amount of points. So unlike the domain and the range here, I cannot just list off points. Okay? I have to show the infinite possibility of all these infinite points. And to do that, I'm going to use a compound inequality. So here my domain will be all of my x's between 2 values. And my range is going to be all my y's between 2 values. Remember how we talked about when we use these symbols? It's like between this and this, and between that and that. And what we're going to do is we're going to look at our graph and figure out what are my x's actually between. What are those numbers? Okay, so I look at my graph. What I will do is mark off on my x-axis and my y-axis where the graph is contained. Okay, so these are all points. This point here is like -3, 4, right? Well, that means the graph starts having x values at -3. And it has the greatest amount of y values up here at 4. Well, going all the way over, we have all these x values and y values. We get here to the end. I notice here my x values stop there and my y values stop here. since this isn't the x-axis, these will be the two numbers that my x's are between. That's -3. This is 4. So I put -3 and 4. That's where my x's are between. For my y's, they're between -2 and this 4. We're going to practice these. I'd like you to try them for your homework. We will practice them next class period, which will be Friday. I will see you guys next on Friday. Thank you, Ms. Sanchez.
She took, I'm not done with my test, but she took it to bring to you.
Great.
Hi,
Thank you.
this kid's done. She, as she told you, is not.
She's not done yet. Okay. Cool. Thank you. Good. So, didn't take you that long.
No.
Yeah. We should be able to finish, Mr. Head, but I don't want you to rush.
I do have a question. I don't know if you can answer it or not.